Welcome. Today we are focusing on topic 3.7 of the AP Statistics curriculum, carrying out a test for a population proportion. By the end of this lesson, you will be able to calculate the necessary components of a significance test and, more importantly, justify a statistical claim using your results. In our previous lessons, we discussed how to set up hypotheses and check conditions. Now we are getting into the math and the conclusion phases of the process. When we carry out a test, we are essentially asking, if the null hypothesis were actually true, how likely is it that we would see a sample proportion as extreme as the one we just observed? To answer this, we use a test statistic. For a population proportion, this is a z-statistic. Here is the formula for our z-statistic. Let's break down this formula. P hat is your observed sample proportion. P0 is the claimed value from your null hypothesis. Notice the denominator. We use p minus 0, the null value, to calculate the standard deviation of the sampling distribution. This is because we are operating under the assumption that the null hypothesis is true. This z-statistic tells us how many standard deviations our sample proportion is away from the null mean. Because of the central limit theorem, if our conditions are met, this statistic follows a standard normal distribution. Once we have our z-statistic, the next step is to find the p-value. The p-value is the probability of getting a test statistic as extreme as, or more extreme than, the observed value assuming the null hypothesis is true. For a one-sided greater than alternative hypothesis, the p-value is the area to the right of our z-statistic. For a less than alternative, it is the area to the left. And for a two-sided not equal to alternative, we find the area in one tail and double it. The smaller the p-value, the stronger the evidence against the null hypothesis. It suggests that what we observed would be very unlikely to happen by pure random chance, if the null were actually true. Think of it like this. If a p-value is 0.01, there is only a 1% chance of seeing our sample results just by luck. That makes the null hypothesis look pretty suspicious, doesn't it? To make a decision, we compare our p-value to a predetermined threshold called the significance level, or alpha. The significance level represents the maximum probability we are willing to accept of making a mistake by rejecting a true null hypothesis. Common values are 0.05, 0.01, or 0.10. If our p-value is less than or equal to alpha, the result is statistically significant. We reject the null hypothesis. This means we have found convincing evidence for the alternative hypothesis. If the p-value is greater than alpha, we fail to reject the null hypothesis. We haven't proven the null is true, but we simply don't have enough evidence to ditch it in favor of the alternative. It is a common trap to say we accept the null. In statistics, we never do this. Think of a court trial. A not guilty verdict doesn't prove innocence. It just means there wasn't enough evidence to prove guilt. Similarly, failing to reject the null means the evidence wasn't strong enough to support the alternative. We have now covered the logic behind the decision-making process. You can now compare p-values to alpha to make a formal decision. Let's put this into practice with a full example. Imagine a large high school where the principal claims that 80% of students support a new cell phone policy. A student reporter believes the actual support is lower. They take a random sample of 100 students and find that 72 support the policy. Let's test this at a 5% significance level. First, we state our hypotheses. The null hypothesis is that the true proportion is exactly 0.80. The alternative hypothesis is that the true proportion is less than 0.80. Next, we identify our sample proportion, p hat. Our observed value is 0.72. Now, we calculate the z-statistic using our formula. Plugging in our values, we get 0.72 minus 0.80, divided by the square root of 0.8 times 0.2 over 100. This simplifies to negative 0.08 divided by the square root of 0.0016. Finally, negative 0.08 divided by 0.04 gives us a z-statistic of negative 2.00. Our test statistic is negative 2. This means our sample result is 2 standard deviations below the hypothesized mean. Since our alternative is less than, our p-value is the area to the left of z equals negative 2. Using a standard normal table or technology, we find this area. Now, we compare our p-value of 0.0228 to our alpha of 0.05. Since 0.0228 is less than 0.05, we reject the null hypothesis. There is convincing statistical evidence that the true proportion of students who support the policy is less than 0.80. Notice how the conclusion is tied back to the context of the population. Let's look at another scenario, this time involving a two-sided test. A company produces light bulbs and claims that 90% of them last more than 1,000 hours. A consumer advocacy group suspects the proportion is different from what the company claims. They test a random sample of 200 bulbs and find that 174 of them last more than 1,000 hours. We will use a significance level of 0.01. Our null hypothesis is that the proportion is exactly 0.9. The alternative is that the proportion is not equal to 0.9 because the group suspects it is simply different. First, let's find our sample proportion. Our p-hat is 0.87. Now, we calculate the z-statistic. Substituting our values, we have z equals 0.87 minus 0.90 divided by the square root of 0.90 times 0.10 over 200. This simplifies to negative 0.03 divided by the square root of 0.00045, which is negative 0.03 divided by 0.0212. Our z-statistic is negative 1.41. Because this is a two-sided test, the p-value is the area in both tails. We find the probability of being more than 1.41 standard deviations away from the mean in either direction. The probability of z being less than negative 1.41 is 0.0793. So the total p-value is 2 times 0.0793, which equals 0.1586. Now, compare this to our alpha of 0.01. Since our p-value is much larger than our significance level, we fail to reject the null hypothesis. There is not convincing statistical evidence that the true proportion of light bulbs that last more than 1,000 hours is different from 0.90. Even though 0.87 is less than 0.90, it wasn't different enough to rule out random chance as the explanation, especially at such a strict significance level. Let's consider a third example to see how the sample size affects our results. This time, we'll look at a medical study. A pharmaceutical company claims that their new medication is effective for 60% of patients. A researcher believes the effectiveness might actually be higher. They conduct a study with a random sample of 50 patients and find that 35 of them show improvement. Let's use a significance level of 0.05. The null hypothesis states the proportion of effectiveness is 0.60, while the alternative is that it is greater than 0.60. The sample proportion is 0.70. This looks promising for the researcher. Let's calculate the z-statistic to see if it's statistically significant. We calculate the z-statistic by taking the difference between the sample proportion and the null value, and dividing by the standard error. This simplifies down through the arithmetic to 1.44. Our z-statistic is 1.44. Since our alternative is greater than, we look for the area to the right of 1.44. The p-value is 0.0749. Now, we compare this to alpha equals 0.05. Since the p-value is greater than 0.05, we fail to reject the null hypothesis. There is not convincing statistical evidence that the true effectiveness of the medication is greater than 60%. Wait, the researcher found 70% effectiveness in their sample, which is 10 percentage points higher than the claim. Why didn't we reject? The reason is the sample size. With only 50 people, a result of 70% could still happen reasonably often just by chance, even if the true rate was 60%. This illustrates why a large sample size is often necessary to detect differences. To see how power and sample size interact, let's look at that same medical study, but imagine the researcher had a larger budget. Suppose everything remains the same. The claim is still 60%, and the researcher still observes a 70% success rate. However, this time the study used a sample of 500 patients instead of 50. Let's recalculate the z-statistic with this larger sample size. The difference in the numerator is 0.10, and the standard error in the denominator becomes the square root of 0.24 over 500. This simplifies further as we divide 0.24 by 500 to get 0.00048. Taking the square root, we find the standard error is approximately 0.0219, which results in a z-statistic of 4.57. Notice how the denominator, the standard error, got much smaller. This pushed our z-statistic all the way out to 4.57. If we try to find the p-value for a z-score of 4.57, it is almost zero. Since this p-value is much smaller than 0.05, we now reject the null hypothesis. With 500 patients, a 10 percentage point difference is highly unlikely to be a fluke. We now have convincing evidence that the medication's effectiveness is greater than 60%. This comparison shows that the exact same sample proportion can lead to different conclusions depending on the sample size. Larger samples provide more precise estimates and make it easier to find evidence if a difference truly exists. Let's consider a scenario where the significance level alpha is varied. The choice of alpha is a critical decision in research. as it sets the standard for how much evidence is enough. In our fifth example, a university claims that 50% of its students prefer online classes over in-person ones. An administrator thinks this proportion has changed. They survey 400 students and find that 220 prefer online classes. Our null hypothesis is that the proportion is 0.50. The alternative hypothesis is that the proportion is not equal to 0.50. The sample proportion, p hat, is 220 divided by 400, which equals 0.55. Let's find the z statistic. To calculate z, we subtract the null proportion from the sample proportion and divide by the standard error. This gives us 0.05 divided by the square root of 0.50 times 0.50 over 400. This simplifies down to 0.05 divided by 0.025, which results in a z-score of 2.00. With a z-score of 2.00 and a two-sided test, we look at both tails. The p-value is twice the probability that z is greater than 2.00, which calculates to 0.0456. Now, watch what happens when we change our standard of proof, alpha. In case A, where alpha is 0.05, 0.0456 is less than alpha, so we reject the null hypothesis. There is convincing evidence that the proportion is different from 50%. However, in case B, if we use a 1% significance level, 0.0456 is greater than 0.01, we fail to reject. In this case, we would say there is not convincing evidence of a change. This demonstrates that the conclusion of a study isn't just about the data, it's also about the threshold for evidence that you set before you even start. Now that we've seen several examples, let's revisit a critical point about the language we use in our conclusions. In AP statistics, the way you phrase your final answer is just as important as the calculations. A correct conclusion should follow this structure. First, compare the p-value to alpha. Second, state your decision to either reject or fail to reject the null hypothesis. Finally, state your conclusion in context regarding the alternative hypothesis. Always remember that we are making a claim about the population parameter, not the sample. Here are some common errors to avoid. Never say we accept the null hypothesis. Do not say the probability that the null is true is 0.05. And don't forget to mention the population or the context. Let's look at a bad conclusion versus a good conclusion for our previous light bulb example. A bad conclusion would be, the p-value is 0.15, so the null hypothesis is true. 90% of bulbs last over 1,000 hours. This is incorrect, because we haven't proven the null is true. We just didn't find enough evidence to say otherwise. Now, for the good conclusion, because our p-value of 0.1586 is greater than our alpha of 0.01, we fail to reject the null hypothesis. There is not convincing statistical evidence that the true proportion of all light bulbs that last more than 1,000 hours is different from 0.90. This version is perfect. It explicitly compares the values, makes a formal decision, and uses non-definitive language to describe the population parameter. Notice the phrase, not convincing evidence. This is your best friend when you fail to reject. It shows you understand that the alternative hypothesis might still be true, but your data just didn't show it clearly enough this time. Let's apply everything we've learned to a more complex real-world scenario. This example will help us practice the entire process from start to finish. A city transit authority claims that 75% of residents are satisfied with the current bus schedule. A local advocacy group believes the satisfaction rate is actually lower. They conduct a survey of 450 randomly selected residents and find that 322 of them are satisfied. Let's test this claim at a significance level of 0.05. The null hypothesis is the status quo. Satisfaction is 0.75. The alternative reflects the group's suspicion. Satisfaction is less than 0.75. It is important to remember that we check conditions using the null proportion p pi 0, not our sample proportion. Since both expected counts are at least 10, the sampling distribution of p hat is approximately normal. Now for the calculations. First, we find our sample proportion, p hat. Then we calculate the z statistic. The probability of seeing a satisfaction rate this low if the true rate were 75% is about 4.6%. Because our p-value is less than 0.05, we reject the null hypothesis. There is convincing statistical evidence that the true proportion of all residents satisfied with the bus schedule is less than 75%. Notice how close this was. If we had used a significance level of 0.01, we would have reached the opposite conclusion. This is why we always decide on alpha before looking at the data. Let's take a moment to look at a scenario involving a two-sided test with a very small p-value, which often appears in clinical trials or safety testing. A factory produces specialized bolts and claims that exactly 95% of these bolts meet a specific tension requirement. A quality control engineer suspects the machine is out of calibration, meaning the proportion could be higher or lower than 0.95. She tests a random sample of 600 bolts and finds that 556 meet the requirement. Use a significance level of 0.05. First, we calculate the sample proportion, p-hat. Now, we calculate our z-statistic. Plugging in our values, we get 0.9267 minus 0.95, divided by the square root of 0.95 times 0.05 over 600. This simplifies to negative 0.0233 divided by approximately 0.0089. Our z-score is negative 2.62. Since the engineer's alternative hypothesis was that the proportion is different, we must perform a two-tailed test. We find the area to the left of negative 2.62 and double it. The area in one tail is 0.0044. Multiplying by 2 gives a p-value of 0.0088. Now, we compare our p-value to alpha. Since the p-value is less than 0.05, we reject the null hypothesis. There is convincing statistical evidence that the true proportion of bolts meeting the tension requirement is different from 0.95. In fact, it's likely lower. Even if we had used a stricter alpha of 0.01, we still would have rejected the null in this case, because 0.0088 is less than 0.01. This suggests a very strong result. Let's consider one more scenario that highlights a potential pitfall in interpreting results. Sometimes, a result can be statistically significant without being practically significant. A large website claims that 10% of visitors click on a specific advertisement. A marketing manager tries a slightly different color for the buy button, hoping to increase clicks. Because the website has millions of users, they can afford a massive sample size. They test the new button on a random sample of 100,000 visitors and find that 10,200 clicked the ad. Let's test if this small increase from 10% to 10.2% is statistically significant at a 5% level. We calculate our z-statistic. We take the difference between 10.2% and 10%, then divide by the standard error based on the null proportion. Simplifying the denominator gives us 0.000948. This leads to a z-score of 2.11. The p-value is the probability of getting a z-score greater than 2.11. Using technology, we find this is 0.0174. Since 0.0174 is less than 0.05, we reject the null hypothesis. We have convincing evidence that the new color increases the click rate. But wait, the actual increase was only 0.2%. In a sample of 100,000, even a tiny difference becomes statistically significant because the standard error becomes so small. While we are technically correct to reject the null, the marketing manager has to decide if an increase of 0.2% is worth the effort of changing the website. This is the difference between finding a mathematical pattern and finding a meaningful real-world change. Always look at the effect size, not just the p-value. To wrap up our lesson, let's review the step-by-step procedure for any significance test for a population proportion. Think of this as your roadmap for the AP exam. First, you state your hypotheses, define the parameter you are testing, and choose your significance level. Second, you plan by identifying the appropriate inference method. In this case, a one-sample z-test for a proportion, and checking the necessary conditions, randomness, independence, and the large counts condition. Third, you do the work. This involves calculating the sample proportion, the test statistic, and the p-value. The formula for the test statistic is z equals p-hat minus p minus 0, divided by the square root of p minus 0 times 1 minus p minus 0 over n. Finally, you conclude. You make a formal decision to reject or fail to reject the null hypothesis based on a comparison between your p-value and alpha, and you write a clear sentence in the context of the problem. Remember, a hypothesis test is a way to quantify how much evidence we have. It doesn't prove that the null is true or false with absolute certainty. It tells us if the evidence is strong enough to move away from the status quo. To recap our goals, calculate z and p-value, justify a claim by comparing p to alpha, and use correct non-definitive language. You've done a great job today walking through these examples. Practice these steps with your homework problems, and pay close attention to the phrasing of your conclusions. Mastery of this logic is one of the most important skills in all of statistics. Good luck, and I'll see you in the next lesson.